The dashed lines in the diagram represent cross-sections of equipotential surfaces drawn in 1 volt increments. In part A and B, we are to find the work done moving a point charge of 1 coulomb from one place to another. The key to solving this problem is located exactly in the language, find the work done. As we recognize, the relationship is that work, due to a non-conservative force, is equal to the change in total energy. It's a little bit actually of an old-fashioned phrase to ask for the work done by a conservative force, because usually we treat a conservative force as a change in potential energy. Therefore, when the problem asks you, find the work done to, if it references a conservative force, they're really asking you to find the change in energy. And what we recognize is that the potential energy, due to electric forces, can be written as charge times potential. In the first problem, we are asked to move from A to B. We see that A exists on a line where the potential of that line is 1 volt, and the point B is along exactly the same line, also at a potential of 1 volt. Therefore, since we have not changed the potential in moving from one place to another, we have not changed the potential energy, and the work done in moving from A to B is 0. Finally, let's look at the work done in moving from point A to point D. In this case, we have changed the value of potential because point A is found on a line that is labeled as 1 volt, and point D is found on a line that is labeled as 0 volts. Therefore, we can say that the change in potential energy will be equal to the after potential energy, Q times 0 volts, minus the before potential energy, which is Q times 1 volt. Since the charge is 1 coulomb, we find that the change in potential energy in moving from one place to another is negative 1 joule. And that will be equal to work from A to D.